Good morning, everybody. How are you doing?
Excellent.
Monday morning? Yeah. All right, well, who can tell me what we did last time? What did we talk about? Brian. Actually, Alexander. Oh, okay. Brian.
There was that one, the manifold. It's like the point.
That was in the beginning, but what did we talk about most of the time?
Oh, Lotka-Volterra competition.
Okay, what's that?
When there's like two different species and then they're like competing for like the same.
Okay.
How do you affect each other?
What were the species again?
Bunnies and sheep.
Rabbits and sheep. Okay, and this is basically the model we talked about last time. It's a model where two species were competing for the same resources. So sheep compete with the rabbit, rabbits compete with the sheep. The more sheep there are, the harder it is for the rabbits to grow. That's why I'm writing a minus, right? And what we saw is the dynamics was something like this. You could have two steady states where in this steady state there's only rabbits and no sheep. In this steady state there's only sheep and no rabbits. So it's like they're pushing each other away, right? And there was a steady state in the middle. There was some kind of saddle. All right? This situation is a situation that is kind of unfortunate from the point of view of ecology because they're not coexisting, but it's dynamically more interesting. It's dynamically interesting because you can have multiple steady states. Okay? So this has multi-stability, and there's no coexistence between the rabbits and the sheep. And there's another steady state where there's another case, where there's only one steady state that is stable, and the solutions converge towards that one steady state, right? So in this case, there is coexistence. Okay. How is it possible that the same model can give us two different behaviors? What am I changing from this model to this model? The parameters. That's right. For some parameters, you get this behavior. For some parameter, you get this behavior. This behavior is more of a happy ending from the ecological point of view because you have both rabbits and sheep hanging around together, right? This model is dynamically more interesting, and you can have actually it's more interesting also for protein reactions and things like that. We're going to talk more about chemical reactions later, but this is more interesting from a mathematical point of view. Okay, so now we'll talk about predator-prey models. Predator-prey models are models where you have two animals also, but they're not competing for the same resources. In fact, one animal is the resource of the other, right? But the rabbit is the food for the wolf, for example. So we're going to have a rabbit, or a population of rabbits, and we're going to have a population of wolves. So the wolves get in the way of the rabbits, just like before. But the rabbits don't get in the way of the wolves. In fact, the rabbits help the wolves. Okay? And this is what we call negative feedback. Over here, we have what kind of feedback? Positive feedback, because we have a double negative feedback. And here we have a negative feedback. Okay, so negative feedback. Good. Now, let's think about the simplest possible model of rabbits and wolves interacting. This model was created in the 1920s, if I remember correctly, by Lotka and Volterra. Also a predator-prey model. And so the equations are the following. Suppose that X is the predator. In other words, the prey. So the rabbits. And Y is the predator. Or the wolves. Okay, so in the absence of wolves, we're going to assume that the prey grows exponentially. Okay, so the model is going to be x prime equal to, what was exponential growth again? Constant times x, right? So let's write it like a times x. Now, we're going to have, imagine that the wolves and the rabbits are both hanging around in some kind of desert. Okay, it's a big desert. They're all kind of spread out, and every once in a while they meet. You know, like a rabbit's hanging around, and then suddenly it turns over a bush, and then there's a wolf there. Okay, and whenever they meet, let's imagine that the wolf just eats the rabbit. Okay, the rabbit has nowhere to go. So the rate of destruction of the rabbits is proportional to how often they meet, right? The more often the two of them meet, the more often these things die. So now imagine that we have a population of rabbits and sheep hanging around. The likelihood of them meeting is proportional to the product of the two. Okay? X times Y. How is that? If you have twice as many rabbits, then there's twice as much likelihood that they're going to meet at any given time. And this product is twice as big. If there's twice as many wolves, same thing, right? This thing is called, in chemistry, it's called the mass action model. The rate of change of something is proportional to the product. But we're not talking about chemistry, so let's not mention this mass action too much. But this has to do with the rate of, or the likelihood of the two species meeting. So this is likelihood of species meeting at any given time, within an hour, okay? The likelihood that the wolf meets a rabbit is proportional to that product. Okay, so, and should I put a plus or a minus in here? Minus, because the sheep are getting eaten up. Sorry, not the sheep, not the rabbits. Okay, and here I'm going to put a constant because, you know, this thing doesn't have the right units, and we said it's proportional, it's not the same as it being the same, so constant times that. Okay, now, as far as the wolves are concerned, it's the opposite. The wolves grow by meeting. The only way that wolves can grow is by meeting rabbits. So we're going to put the same kind of term, but positive. Because the rate of production of wolves, if you will, is proportional to the rate at which they meet. So we write C times XY. I'm sorry. No. I'm going to put this in here in the end. Minus plus D times XY. Okay, and in the beginning I'm going to put what the wolves would do in the absence of rabbits. Okay, so here Lotka-Volterra introduced a very simple situation. They just die out. Okay, they just die out in a very simple way, minus C times Y. So if there's no rabbits to make them support, the population of wolves diminishes exponentially. That's not very realistic, okay? The wolves don't just die exponentially if there's no rabbits. But unless you want to take into account things like the age of the wolves and whatnot, which would make the model much more complicated, this is basically the simplest thing you can assume. There's some kind of half-life for the wolves. It's like they're radioactive material and they start diminishing, right? It doesn't really make sense, but there you go. So this is the model, very simple model. Again, in the absence of wolves, these guys grow exponentially, and there's these interaction terms, okay? So it's almost as simple as you can imagine it. And so what we're going to do is we're going to analyze this model. Do you guys have any questions about the model? Yes, Brian?
Is there a reason why are C and D not the same? Because
very good question. Okay, how is it that B and D are different terms? Why don't we just use the same? Okay, well, think about it. B has to do with the effect on the rabbits of one interaction. Let's say each interaction kills one rabbit, right? Could you say that each interaction produces one wolf? Not quite, right? The wolf needs to eat multiple rabbits to make another wolf, in some sense, right? So D is going to be, in this case, smaller than B, right? Because the effect of the interaction on the rabbits is larger, B, than the effect of the same interaction on the wolves. Now, if it wasn't rabbits but cows, right? That's a different story. You got a bunch of wolves, a cow gets killed, and then a number of wolves can have dinner, right, with the same cow. Then the parameters would change, right? So in the case of rabbits, you would think the B is bigger than D. In the case of cows, you would have a D, for example, larger than the B. Okay? Sure. Any other questions? Okay. All right, so very simple model. Let's try and analyze it. So I'm just going to write did I write it? Okay, I didn't write it over there. So if y is equal to 0, x prime is equal to ax is exponential growth. So we're building off of a model that we already know. That's important, right? You guys have seen a pattern here. We always kind of use the original model, exponential logistic, and we expand it to include other things, right? Okay, so let's figure out the steady states of this model. Who can tell me a steady state, like the simplest possible steady state, or a steady state?
Y and x equals 0.
That's right. So xy can be equal to 0, 0, and that's a steady state. Intuitively, that makes sense because if there's no rabbits and there's no wolves to begin with, you cannot have wolves coming out of nowhere and rabbits coming out of nowhere. And if you look at the equations, you'll see that x prime is equal to 0 and y prime is equal to 0, so it's a steady state. Okay? So there you go. That's the simplest steady state. Now let's suppose we want to find another one, okay? So suppose, let's say that x is different from 0, okay? We have some rabbits to begin with. So if we're at steady state and x is different from 0, what happens? Well, let's look at the first equation. We have x multiplied by something, right? X multiplied by a minus by. If x is different from 0, that means that that other term has to be equal to 0. So from the first equation, we can tell that a minus by is equal to 0. That means that y is equal to a over b. Okay, so in particular, this guy is different from 0. Okay, now in the second equation, this equation right here, you have y multiplied by something, minus c plus dx. And y is different from 0. That means that the other thing has to be equal to 0. Right? Also, we have minus c plus dx equal to 0. Okay. Therefore, x is equal to c over d. Great. So notice that the assumption alone that x is different from 0 leads to this steady state and nothing else. We can do the same. If we assume that y is different from 0, we get to the same steady state. So we really only have two steady states, this one and that one. What about the Jacobian? Okay, so we have the steady state C over D, comma, A over B. What about the Jacobian of this system? Does anybody want to try? Wilson? Yes. The Jacobian in general of that dynamical system. No, just tell me.
Oh, A minus BY would be the top left corner.
Sure. A minus BY.
And then on the right it's going to be negative BX.
Okay, negative BX.
And bottom left is going to be negative C plus DX. Oh, I'm sorry, negative dy.
Plus dy, right?
Yeah, positive dy. Left is going to be negative C plus DX.
Great. Awesome. So let's calculate the Jacobian at the two different steady states we have. So at 0, 0, Nelson, what is the Jacobian?
A 0, 0, negative C.
Okay, so let's look at this this steady state and let's try and figure out. So imagine we linearize around that steady state and we're trying to figure out what that dynamics looks like, right? So what are the eigenvalues of this system? Patrick. So eigenvalues are A and negative C. Can you tell me the eigenvectors? Do you know what the eigenvectors are? For example, the eigenvector for this one?
That would be 1, 0.
Yes. 1, 0. And the other one?
0.
So we even know the eigenvectors and the eigenvalues. This is a very simple matrix, right? That means the system looks like this. The linear system, let's say, I'm going to use a new variable, whatever you want to call it. It's a system associated with this matrix, right? You have eigenvectors with eigenvalues A and minus C. And so the dynamics is like this. What's this called again? It's a saddle, right? So this is the linearization around around 0, 0. What about we linearize around that second steady state? So at the steady state, what was it? C over D, A over B? Does anybody want to try? Jonathan? No. What's your name again? Jonathan. Yes. Okay. Do you want to tell me what the Jacobian is at that point? Okay, so A minus B times Y, but Y is this, right? Yeah. So when you write A over B in here, the B cancels out, so you end up with an A here, and A minus A is 0, right? Great, so we get a 0 here. Who would have thought, right? Okay, what about the next one? Okay, what about over here? wait, what did you say? AD over B, yes, sure.
And then the other one would be 0.
It's also 0 because when you plug in C over D over there, the D cancels with the D on top. So you end up with a C and minus C plus C is 0, right? Great. Also a nice simple matrix, right? Okay, so let's try and figure out the eigenvectors or the eigenvalues of this thing. This time it's not so easy. We cannot just see them right away, or maybe you can. So, but what we're going to do is I'm going to write down the determinant of this thing. Okay, so the determinant matrix is minus lambda minus BC over D, dA over B minus lambda. Determinant of this thing is minus lambda times minus lambda is the same thing as minus lambda squared is the same thing as lambda squared, plus there's some cancellation. This times this guy times this guy. It's B cancels with the B, D cancels with D, and you end up with an AC. Okay? That means that the eigenvalues are plus or minus square root of AC times I. They're imaginary. Okay? Because they're imaginary, the dynamics is what?
Around the linearization.
The linearization looks like this, right? This is the system Z prime equals J times C, the linearization of the system around that steady state. Okay? Now, does that mean that the original system must look like that? It does not, right? Why not?
Because of the
Hartman-Grobman, right. Hartman-Grobman theorem is a theorem that guarantees that the nonlinear system looks qualitatively like the linearization. It's the whole point of linearizing, is to get a good idea of what the qualitative behavior is. And the only assumption we have to make is that the linearization is hyperbolic. In other words, that there's no eigenvalues on the imaginary line. But in this case, there are eigenvalues on the imaginary line. That means that the Hartman-Grobman theorem cannot be applied. Okay? It doesn't mean that the system doesn't look like this. It just means that the Hartman-Grobman theorem cannot be applied. Okay? As it turns out, it looks like that. The linearization does look like this. But you cannot conclude it from the theorem, okay? I'm just telling you from, you can actually, at this point the analysis kind of like stops. You cannot conclude the dynamics of the system by looking at the linearization because the theorem doesn't apply, but it is still true that the dynamics looks like that. So this steady state looks like this, and this steady state over here looks just like the linearization. Let's see. Wait, where is it? Oh, there. Let's see. Okay, so whatever that system looks like, that's how the original system looks like around the steady state. Okay? So this is now the rabbits, sheep, and when you run this thing in the computer, you'll realize that the solutions do look like this. So it is a center. It does look like the linearization. You just have to be a little bit careful because it doesn't follow from the theorem. But it does look like the linearization around that point. That means that, let me draw another solution. For example, around here. The solution that starts here starts going around in a circle and then ends up there again. What happens when you run this thing over time? Oh, I'm sorry, this is not sheep, this is wolves. Okay? This is X. This is Y. when you run it over time, you'll see oscillatory behavior. This is, let's say, x over time. And if you wanted to plot the wolves over time, you can find something like this. So sure enough, you see oscillations over time. Remember that we said last time that negative feedback can give you oscillations. Okay? Now, so do you have any questions? No questions? Yes, Wilson.
The way that graph looks, the amplitude of the green one, is it supposed to be bigger than the blue one?
I actually drew it on purpose a little bit bigger. It doesn't have to be the same. If they were at the same amplitude, this guy would look like a circle, right? But this could look like an ellipse, right? In which case, in this case, the rabbits have a bigger amplitude than the wolves.
How do you know they're out of phase?
Sorry?
How do you know that they're 180 degrees?
Okay, so also a good question, right? So, and in this case, okay, if they were on phase, if they go both up and down at the same time, then the graph of both of them together would look like a straight line, like this, right? So the fact that it looks like a circle means the phase cannot be the same. Okay, that's a good question. So actually, the way to imagine this is when let's say there's no wolves. Okay, so you start out, let's say around here, because there's not a lot of wolves. Just a little bit of wolves. If there's no wolves, you just have rabbits. Nothing can happen, right? Nothing interesting can happen. Let's say that just a little bit of wolves. So the rabbits start growing without the wolves giving them a hard time, right? But after a while, because there's so many rabbits, the wolves are having a great time because they have so easy time chasing rabbits. So the population of wolves starts going up, and it goes way up. And at some point, there's too many wolves. Too many wolves to be sustained by that number of rabbits. So the population of rabbits starts going down, because there's too many wolves and they're eating them. So the population of rabbits goes way down, and the population of rabbits goes down to the point that the wolves remaining cannot survive on that small number of rabbits. So the population of wolves goes down, and so on and so forth. Okay, so it's like they're promoting and inhibiting each other, so they're always overshooting, going way up, going way down, going way up again, way down. Okay, that's what happens with negative feedback. Let me give you another example of negative feedback. You go to a hotel, let's say a cheap hotel, okay, and you go into the shower, you turn on the shower, and the water is too hot. Okay, so what do? You lower the shower, what's it called? The knob? Yeah, okay, the knob. You lower the knob. Okay, but you wait for a while. You keep lowering the knob, and then after a while, the water starts coming out too cold. Has that happened to you? So what happens is that you basically do the opposite of what the temperature says. If it's too hot, you move it colder. If it's too cold, you move the knob hotter, which is negative feedback, right? That's what negative feedback is in this case. And negative feedback causes oscillations. You move it hot, the water comes out too hot, so you move it down, then it comes out too cold, and so on and so forth. So the temperature over time is oscillatory. Of course, you probably pick it up after more than a moment and slow down or do something about it, right? But other than that, the dynamics would look oscillatory over time. Same thing, same idea. Okay. Any other questions? Okay, so now let me tell you my criticism of this model. I think this model is too cute. It doesn't, things don't work like that in practice. What I don't like about the system in particular is this idea that the dynamics stays in the same orbit. If you start here, you start running around and you end up in there as well. And if you started here, you were going around in this circle, okay? And you could never change from one orbit to the other. It's like you're stuck in that orbit. And biologically, that doesn't make sense because there's noise, there's, things are not as nice as that. It would be very unlikely for the orbit between rabbits and sheep to stay always the same. Okay. So to show you that this model is actually too cute for its own good, and that it's not really all that realistic, and that there's serious problems with it, I'm going to make a small change to the model, and I'm going to show you that this whole thing, in a sense, breaks down. What I'm going to assume is we're going to change one of the assumptions from before. It's this assumption right here. We assume that in the absence of wolves, the rabbits are growing exponentially. So let's say that they don't grow exponentially, but what is the other kind of growth? Logistic, okay? Let's change this exponential growth to a logistic growth and see what happens. So let's do it. So let's see, can we just change those terms and make it into a logistic model? As a matter of fact, we can. Now, so slight tweak to the model. Assume logistic growth in the absence of wolves. I always want to say wolves with FNS, but anyway, that's I guess how it's worked, how it's written. So x prime equals, so this is rabbit in the absence of wolves. How is that again? It used to be ax, right?
Yeah.
So now we're going to write ax times 1 minus x over carrying capacity, right? And the rest is exactly the same as before. Minus b xy, and this is y prime equals minus cx plus d xy. Okay, so now notice that if we make k really, really large, you essentially, in a sense, converge towards the original model, right? If k is really huge, like 1,000,000, then this term is vanishingly small, and the dynamics looks a lot like the original dynamics. Okay. So let's calculate the new steady state. New steady state that is non-zero. I mean, the steady state 0 is still there, not a problem, right? But what happens if we set x and y different from 0 and we're looking for a steady state? Well, since x is different from 0, we have that this is equal to 0, and this is x times something, minus c plus dy. Okay? Because x is different from 0, we have that, minus c plus dy must be equal to 0. You agree? Okay. That means that y is still equal to c over d. Just like before, okay? What about the other steady state? Well, the other steady state is a little more complicated. Now we have that oh, I see.
It should be negative
Y.
CY, not CX.
Yeah, dy.
for y prime.
CY. Oh, thank you. Thank you, that's a good point. So then let me do this. So then this is the x? Yeah, thanks. Okay, thanks for pointing that out. So since we have a non-zero steady state, let's assume that y is different from 0, so x is equal to c over d, just like before. Okay? Now let's plug in x in this equation here. Okay, and we set that equal to 0. So a times c over d times 1 minus c over dk minus b times c over d times y is equal to 0. Okay, so that means that actually you can cancel out the c over d on both sides, and you get that y is equal to what? A over b multiplied by 1 minus c over dk. Okay. In particular, notice that basically we're assuming that the parameters are such that this thing is bigger than 0. If this is not bigger than 0, then we're essentially back to a system that is only really has one steady state, is not biologically realistic. We want our non-zero steady state to be positive, right? So we're assuming that this thing is bigger than 0. And so therefore, 1 minus c over dk is bigger than 0, which is the same as saying that dk is bigger than c. Okay? So we are setting the parameters in such a way that dk is bigger than c. All right, now let's find the Jacobian of the new system. Who wants to try? Maybe Daniel? Well, you know what? Not sure. I mean, we could compute the Jacobian, but you see. Yeah, I mean, let me save some time. You can compute the Jacobian around the new steady state. And I'm just going to write it down. So you calculate the Jacobian and then plug in those numbers over there, and you get minus a c over dk minus bc over d times okay, this is dab, like this, times 1 minus c over dk and 0. Okay, now what is the trace of this Jacobian matrix?
Negative AC over dk.
Okay. And is that positive or negative?
Negative.
Okay. What about the determinant? It's what?
It's a positive number.
How do you know?
Because the main diagonal is 0,
Okay.
and then the other diagonal you multiply by a negative number. So that makes BC over A positive. So that's a positive number times another positive number. Since 1 minus C over dk, we call the positive number.
Okay, excellent. So that analysis over there, you know, we're now going to use it. This guy over here is bigger than 0. Okay? We're assuming that it's bigger than 0. And since this is bigger than 0, then this whole thing is bigger than 0. Okay? Great. So now, Brian, Kwan, what can I say if the trace is negative and the determinant is positive?
That it has 2 eigenvalues less than 0, the real.
2 eigenvalues less than 0, exactly. Actually, I'm not sure the real part is less than 0. So in other words, the matrix is stable, right? Stable dynamics. What that means is that this is the dynamics around of the original system. And by the way, now I'm not fudging around because this system is hyperbolic. This linear system is hyperbolic. I can actually use the Harpan-Grobman theorem, and for sure I know that the original system looks like this. It is a saddle at this point. Okay. It has stable dynamics around this point, because that's exactly what's predicted by that system, stability. And it actually has a new steady state over here, which is at K. Do you remember this? That because we're introducing a logistic term, if in the absence of wolves, the system looks like a logistic system, right? So now it has a stable steady state at K. In the absence of wolves. Okay? But now what happens over here is completely different. We have our saddle, same as before, but now we have that steady state is actually spiraling in. Yes?
How do you know it spirals that way instead of the other way?
Okay, or even how do you know it spirals this way as opposed to the other way? Or even how do you know that it spirals at all? That would follow from a null-Klein analysis. Okay? If you do the null-Kleins, let's say the null-Kleins look like this, and you show that this points like this and this points like that, then you know that it's spiraling. On the one hand side, you know that it's spiraling. On the other side, you know that it's a stable system. So the only possible behavior is this. Okay? This is something that maybe I should have stressed, or I could stress more before in the past few lectures, that null-Klein plus that thing can tell you the actual behavior. If the null-Klein was let's say, like this. Okay. Basically, the arrows are all pointing in, and the system is stable. You know that it's a stable node. It doesn't actually oscillate. But if it looks like this, then the system actually oscillates. So you can tell whether it's oscillating or not, and you can actually tell whether it's a saddle or not by looking at the null-Kleins. Okay, so now notice that we make a very small change to the system. We said, let's introduce this logistic term. K can be very, very, very large. And in fact, K is kind of always there. You know, there's no such thing as a population of rabbits that can really grow exponentially with no end. So you can introduce K as large as you want, 1 million or 1,000 or however many million you want. And the system still predicts the behavior of the system is like this. So that is bad news for the Lotka-Volterra model. Okay, what it means is that the Lotka-Volterra model is too, it's too simple. It doesn't really, it's not robust to very small changes to the model. Okay, good models are models that should be able to have the same behavior, even if you make tiny changes like this. And let me insist that change is tiny. For example, if you make k very, very large, like 1,000,000, then this matrix becomes very, very similar to the other matrix we had. Do I still have it here? Oh yeah, look at this. Okay, so look at that matrix over there all the way in the end and see what happens when k is very, very small. When k is very, very small, this term becomes 0. Okay, that term becomes BC over D, which is the same as it's over there. That thing becomes this because when k becomes very, very tiny, right? The second term becomes 0, and that is 0. Okay, so again, when k is very, very big, very, very big, that new model becomes the old model. Okay, and no matter for what value of k, the system has that spiraling in behavior. All right. So there you go. So this is an analysis involving two different models, one more, let's say, more precise than the other, that have very different behaviors. So it's like a cautionary tale. And on the way, we also talked about oscillations and this classical model of predator-prey dynamics. So, questions? No questions? Brian? No? Okay, but today you guys have some very good questions. So keep it up. All right. See you guys on Wednesday.